there's plenty of research related to those nuclear and renewables. You want to address some of, since you're the director, and your perspective from a U.S. point of view?
Well, let's see. Yeah, you're right. We have R&D at Oak Ridge that touches on almost all of these areas. The lab began its life focused on nuclear, and particularly both nuclear energy and also other uses of nuclear, like isotopes for medicine and that kind of thing. And we still do a lot of that. I mentioned the modeling and simulation, which is one example. So there's this CASTLE project is led by Oak Ridge, but it involves other universities, University of Michigan, MIT, North Carolina State. There are other Department of Energy labs, Idaho, Los Alamos, and Sandia, and also industry, Westinghouse, the Electric Power Research Institute, and Tennessee Valley Authority is providing us the data on the reactor operation. And we're making real progress there. One of the really exciting things that just happened this past year was the suite of tools are called VERA, the Virtual Environment for Reactor Applications. The VERA tools was used by Westinghouse to simulate the startup of the AP1000 reactor. And the reason that's kind of exciting is CASTLE's focused on existing reactors. So in the US there's about 100 light water reactors, about 60% of them are pressurized water reactors. And around the world, it's about that 60% that's PWRs, which is what VERA is good for. So there we're trying to simulate these operational things, like going to high burn up fuels, build up of deposits on fuel elements, things that happen in the water flow that can damage the reactor, that kind of thing. But having developed that toolkit, you can now apply it to a totally new design, which is also a pressurized water reactor, the AP1000, and simulate the startup of the first AP1000, which will happen in San Men, in about 2 years. And so that's sort of a real test, because now we're not simulating existing reactors and looking at stuff that's already been done. This is now real prediction. So we'll find out whether or not it's right in 2 years' time, but really unprecedented fidelity. So that's kind of exciting. There's a lot of interest in accident-tolerant fuels, particularly after Fukushima. And the problem at Fukushima was because the fuels that we use are clad in zirconium, and at high temperatures, zirconium pulls the hydrogen out of the water. And the hydrogen bubbles up, and the explosion that you saw was the result of that hydrogen collecting and then exploding. So you'd like to have a fuel cladding that didn't have that behavior, and it doesn't have to get that hot. I think it's like 800 degrees. And so we're looking at encapsulating the fuel in things like silicon carbide, which can withstand much higher temperatures. And that's what we mean when we say an accident-tolerant fuel, something that if you had a loss of cooling, which is what happened when the power went out at Fukushima because of the tsunami, the reactor temperature could go up, way higher without having that release of hydrogen and the resulting explosion that damaged the containment and caused the release. So that's another activity that we're very active in. In terms of fusion, Oak Ridge is actually responsible for the US contribution to ITER, so we're managing the project that's fabricating that 9% that gets shipped to Cadarache. So we're very engaged in that. We're also very engaged in some of the materials problems that will become important after. For some of the other areas that I talked about in terms of grid and renewables and so forth, the activities at Oak Ridge that are most important to that have to do with materials. We're fundamentally, amongst all the things we do, we're a materials lab. And most energy problems, if you scratch the surface underneath, they're materials problems. And so we have, condensed matter physicists and solid state chemists and polymer experts and the whole range of that are working on the materials problems. In terms of, and that's, I think, representative of what's happening in the research community across the US is, people are working on all different aspects of these problems. Probably the area where the least is happening is on the carbon capture and sequestration. And you have these demonstration projects, which, as I said, are mostly coupled to enhanced oil production. There's not a lot of work being done in some of the fundamental science about what happens when you put CO2 into geological formations and so forth. So that's probably the biggest gap.
Another question? Yeah, please.
The media and environmentalists make a lot of noise about fracking, but it seems to be something that industry and big business favor. I'd be interested in your perspective on that.
Well, right now, the U.S. is, and to some extent parts of Canada, are the only area where fracking has had a big impact so far. In the U.S., it's had a huge impact. As I said, the CO2 emissions in the U.S. have actually been going down because coal plants are being replaced by natural gas. And there's about a factor of 2 benefit in terms of CO2 emissions. And it's totally driven by price. I mean, there has been a move to regulate power plants so that utilities basically can't build coal plants because of the EPA restrictions, which is basically a natural gas standard in terms of CO2 emissions. But and politically, people have been, from coal-producing states have been complaining, saying, well, the EPA is a war on coal. The same thing would be happening even without the EPA, just because of the pricing. It's a really easy decision right now with natural gas prices so low. And the other thing that it's had an impact on is when you extract the natural gas, you typically get a lot of liquids as well. You get what's called natural gas liquids. It's basically petroleum. And in fact, because the oil price stayed high, the natural gas liquids are more than the natural gas. So in some cases, they just flare the natural gas, burn it, and collect the natural gas liquids because they're pinned to the price of petroleum. And so as a result of that, petroleum imports in the U.S. have gone down, and for the first time in 20 years, petroleum imports are less than 50% of consumption. And you have to go back to 1994 to get a time when that was. So huge economic impact in terms of the balance of trade deficit of the U.S. So natural gas has been quite transformational, but it has not yet happened anywhere else. And that's not because of the geology. There are plenty of other places in the world that have the same type of shale formations and so forth that the U.S. does. So in principle, the shale gas is there. The barriers are, first off, it's a more complicated technology, and U.S. industry has been working on it since the 80s. In fact, with federal government support, the R&D dollars in the 80s developed the technology of horizontal drilling and fracturing. Wasn't industry because it made no economic sense at all in the 80s. And so it happens that U.S. industry has a better understanding of that technology, and it's not present in industry in other countries yet. There are also things to do with the way that land mineral rights work, where in the U.S. it just happens that the legal framework around mineral rights allows exploitation of it. There is some public controversy. So in some states, for example, in New York State, they basically said no fracking. And in Texas, they basically said as much fracking as you want. And there are some challenges in terms of water use. And there are solutions, though, and some of them come quite naturally. One of the big costs has been just trucking the water in, so there's a big economic driver for industry to recycle the water. And that's starting to happen. There are concerns about the chemicals that are used and whether or not that could damage the aquifer. There are also concerns about if you have what are called fugitive methane emissions. Methane is a very powerful greenhouse gas because of the rotational modes in the molecules. And if you have significant loss of methane through the extraction process, then the CO2 benefit from burning methane against coal is wiped out by the methane impact. That is very difficult to estimate. And so there are wide error bars on the fugitive methane emissions, and it's not yet clear, what the reality is. Now, some of that, I think, can be handled by regulatory means, because generally, if you do things well, and you're careful with the casing that you use in the borehole and so forth, you don't lose a lot of methane. If you do it in a sloppy way, you'll lose more. So I think that there are probably regulatory ways of addressing the fugitive methane emissions. No form of energy comes free of environmental consequences. And almost every form will have people who oppose it. I mean, in Europe now, there are people who are saying no more windmills. Don't want any more windmills. You have a lot of concerns about damming rivers and what are the consequences associated with damming rivers? What are the effects on fish populations? What about the displaced people who are flooded out and the forests and all that sort of thing? Fracking has concerns. The mining of coal is a messy, dirty business and kills more people every year than, any nuclear accident ever has. And of course, you have the concerns post-Fukushima about nuclear. So, there is no form of energy that is without consequence. On the other hand, if you look at the benefit to society and human health and standard of living that comes with energy, there's a value in that. And the fact that we have, because of energy, access to food that doesn't poison us because it's refrigerated, and water that doesn't kill us because we've purified it, and light so that we can read at night, that's a social good. And so I think in the end, it becomes a question of, can you mitigate and minimize the bad social consequences associated with energy production? You will never eliminate them in order to enjoy the social benefits associated with energy use. And my personal belief is that actually fracking is on the relatively easy scale in terms of mitigating the social consequences. It's much harder to mitigate some of the social consequences associated with some of the other forms of energy. And sometimes it's a lot easier to say no to things, but if you want the lights to go on when you flip the switch, you have to be prepared to say yes to something.
I have a question. Yeah, please, Professor.
So Tom, you mentioned that technology really underpins a lot of these energy efficiency and so on. I was just wondering, what is a typical cycle of a technology development? So you mentioned, for example, fracking. That technology was, the investment started in the 1980s and took about, 10, 20 years? What is the typical technology development cycle?
Well, so another example is refrigeration. I mentioned that refrigerators are 3 times more energy efficient than they were in the 70s. That was not actually a eureka moment where someone invented a whole new type of refrigerator and dropped the energy consumption by a factor of 3. That was a few percent a year for 40 years. And wind is the same story. In the 70s, a windmill took more energy to produce than it produced over its entire operating life. So if you looked at the amount of energy to, put together, make all the materials and erect the windmill, you would never get net energy out in 1975. Now, a windmill gets energy payback in like 13 months. Again, no fundamental eureka breakthrough where suddenly whole new, the windmills aren't that different than they were in terms of, it's a thing that spins around when the wind blows on it. No fundamental new idea. But again, it was about 3% a year over decades, magic of compound interest, and, scaling it up. So now you go to these enormous wind turbines where the blades are longer than a than a wide-body aircraft, carbon fiber, the turbine and improving the efficiency of that, managing the vibrations so that it lasts longer, so you have more opportunity to produce energy. So in a lot of these areas, it's actually the technology cycle is kind of relentless incremental improvement. Now, in some areas, we really need a breakthrough. electrical energy storage, we could really use a breakthrough. I mean, we'll continue to improve, but if you want to get to a, you know, a battery that doesn't cost $10,000–$15,000 and has a 300 or 500 mile range, I mean, you probably, you know, you'll run out of steam just by tweaking lithium-ion batteries. So there's some areas where we could use a breakthrough.
Okay, so last question. Okay, yeah, because
I work for nuclear industry for over 40 years, so I appreciate some of your comment on the particular nuclear fuel area. So I don't want to overreach top T or not, but the first thing we do to power operate. One of the things before we do that, we do the raw generator rewind and turbo overhaul. That right away uses the same amount of fuel, and you produce more energy. Is there? I believe there's a lot of work can be done out there based on current conventional power plant to improve the efficiency, in other words, produce more power using the same amount of fuel, which means that we'll continue to keep the low carbon.
No, you're absolutely right. For example, if you have steam turbines that operated at higher temperature, thermodynamic efficiency improves right away, right? So
the question is, any technology, a lot of R&D on that area too?
Well, that's the steam turbine operating temperature question. That's a materials question. You know, can you produce a steel, you know, that will have the right properties in terms of creep and all these sorts of things, so that it can operate 100 degrees higher? And if you can increase that, you know, you can start to, and then it doesn't matter whether it's a nuclear power plant or a coal plant. You know, in the end, all the power source is doing is making steam, and you improve the thermodynamic efficiency. You know, can you get to 45–50%? And you know, thermodynamically you can. The problem is the materials. Yeah, right. Yeah. And so that's a you know, it's a bit, you know, it's one way to as you continue to use fossil fuels, you know, for some period of time, it's one way to get there. And of course, you know, there's an economic benefit if you can make it work.
Okay, so let's thank Professor Mason. So on behalf of the university, Professor Alice present a small gift to show our appreciation. Okay, so thank you very much for your support.